Thank you. My
Yes,
name is,
go ahead. Thank
oh,
you.
thanks. Yeah, my name is William Cramer, and I'm a postdoc at Arizona State University. I'm working with Allison Noble, who you heard from earlier. And I'll be talking about searching for kinematic signs of ram pressure stripping in high redshift, specifically redshift of 1.6 clusters, with resolved ALMA observations of molecular gas traced with CO2 to 1. So this has been covered extensively at this conference now, but I feel like I should just go quickly over why you should care about ram pressure stripping. It's been found, at least in the low redshift universe, to drive galaxy evolution and color migration, especially in clusters. So this is a classic figure from Dressler in 1980 showing that as the density of the environment increases, the quenched fraction also increases. And that's not solely due to ram pressure, but it's been found that ram pressure is a major driver of this evolution in dense environments via star formation quenching by stripping of gas. However, more recently, it's been found that ram pressure can have an even more complex role in driving galaxy evolution. For example, it's been found by a number of people. I just show one figure at the top here from Roberts in 2020 that can trigger star formation, especially asymmetric star formation on the leading side of a galaxy. And overall, as Volcani in 2020 found, ram pressure stripped galaxies have been found at the relative peak of pressure to overall have a higher star formation rate than non-stripped galaxies and clusters. So major question is ram pressure active in driving evolution in high redshift clusters? In high redshift clusters, the properties of the ISM or ICM are relatively unconstrained still, and cluster masses are lower. So it's still unknown what role ram pressure plays in the high redshift universe. And ALMA affords us one of the best chances at trying to identify ram pressure stripping by allowing us to study the molecular gas in disks. So on the right here, I show some examples of head-tail morphology, which are classically used to identify ram pressure stripping from Allison Noble's 2019 paper. But tails in general are hard to detect because they're low surface brightness and they're hard to resolve, whereas disks are easier to detect. So if we can use the molecular gas in a disk and identify a signature of stripping, that can be an easy way to identify stripping on large scales and clusters without significant integration time. So the question is, what effect does ram pressure have on the molecular gas in disks? And one easy way to study this is to look first at the low redshift universe and then see what we can extrapolate towards observations in the high redshift universe. So I searched in the Virgo cluster and observed this galaxy NGC4402. You can see this is an H1 map of the galaxy. There's a head-tail morphology, and the gas is more compressed on the leading side, where I indicate the direction of ram pressure here. Here's just a larger view of this galaxy in HST, where you can see clearly the effects of ram pressure pushing the gas up on the leading side and stripping it out, whereas the more shielded side is not pushed as far by the ram pressure. Just to zoom in to show the dramatic effects of ram pressure on the ISM here, where there's this big plume of dust that's being lifted up and off, and some features that we won't be able to detect at high redshift, but are interesting signs of how ram pressure affects the multi-phase ISM, such as some decoupled clouds of denser gas that appear to be left behind, while the less dense gases lifted up and away, and a lot of young stars, which could be triggered star formation in this region of the galaxy. So as I published in my 2020 paper, we got a full ALMA map in CO2 to 1 of this galaxy at 80 by 150 parsec resolution. And this map covered basically most of the dust that you can see in the HST image, including that leading side plume where you can see the gas being stripped up and away. So with this map, we're able to investigate the kinematics of the molecular gas, both in the disk and the stripped area, to see where we can identify the kinematic signs of stripping. But before I show you the kinematic map, I just want to show you what a normal galaxy would look like. So on the right is just a spiral galaxy from Walter 2008. This isn't a cluster galaxy. This is just showing what a relatively normal moment one map looks like, although there's some disturbances from the spiral arms. You see these V-shaped isovelocity contours, and both sides of the galaxy should be relatively symmetric about the center. In contrast, this is what the moment one map of NGC4402 looks like. On the right side, it looks more like a normal spider diagram. You see some signs of that V-shaped isovelocity contours. However, as you move to the left side of the galaxy, past the green is basically the kinematic center, you see that the shape of the isovelocity contours begins to change. They begin to become more straight. And then as you go towards the plume, you see the signature of the gas being actually pushed out of the galaxy. This is interesting because this is also one of the first signs that ram pressure can actually affect the molecular gas in the disk of galaxies. So I'm just going to illustrate this one more way with a position velocity diagram. And if you're not familiar with radio astronomy, I just want to briefly go over what this is. So basically, a position velocity diagram will plot all the velocities along the line of sight. And I'm going to show a position velocity diagram of the entire disk. So I'm just stepping through the entire disk of the galaxy and showing all the velocities along the line of sight. So at the top is a moment one, and at the bottom is that position velocity diagram, where you can see in contours, I've mirrored the right shielded side of the galaxy onto the left side to highlight how asymmetric this galaxy is, due to the fact that ram pressure is impacting the leading side more than the trailing side. So you can see at about 40 arc seconds in this region, you start to see a clear divergence between the velocity on the leading side compared to the trailing side. And this is interesting because it's not just the plume of stripped gas that's being affected by ram pressure. It's gas further in the disk that we can actually detect this kinematic signature of ram pressure stripping. And finally, just one more way to illustrate this, we built a model of the circular velocity of this galaxy based on the more shielded side, to show in position velocity space where the galaxy begins to show the kinematic signature of stripping. So in contours on the bottom in this movie, you'll see our model compared to the data, which is going to be the surface. So on the right side of the galaxy, that's where the model is based on the data. So you'll see that it agrees well. And it tracks well through the nucleus as well. But when we hit about 40 arc seconds, you can see the shape, the distribution begins to change. And then as you get to the plume, you see a full divergence from the predicted circular velocity at this radius if this galaxy had a symmetric velocity field. And I'll just show this one more time. Yeah, right about here is when you start to see the biggest change in the kinematic shape. Okay, so we've shown that ram pressure can affect the kinematics in a galaxy, and it can be observed at low redshift with ALMA in the molecular gas. But can we detect similar asymmetries with similar techniques at high redshift? Specifically, in my case, I'm looking at a number of clusters at redshift of 1.6. So I'll just show briefly that this is still very much a work in progress, so I don't have any concrete conclusions to give you today. But here's a sample of some of these galaxies that I'm looking at, including the moment one maps on the left and some moment zero on HST images on the right. And I'll just pull out one specific candidate that looks morphologically like it could be a ram pressure stripped galaxy because it has those compressed gas contours on one side of the galaxy and what looks like a head-tail morphology towards the right. And you can see here's the moment one map of the galaxy, the moment zero map, a model moment one map of the circular velocity, which is kind of the same technique that I applied in 4402. This is using the 3D Barolo kinematic modeling software. And then finally, I show a residual map where I subtract the moment one map from the model map. And you can see that towards this more trailing side of the galaxy, you see higher velocity residuals. So green in this case would be zero velocity residual. So this isn't a conclusive result because at high redshift, things are more poorly resolved. But with a large enough sample of these galaxies and looking for these signatures of stripping via the residual map, we can identify if there are signs of stripping in the kinematic signature of the molecular gas. So in conclusion, with ALMA, we've shown that studies of molecular gas can identify the signature of ram pressure in the disk using molecular gas in low redshift galaxies. And we can try to apply the same techniques for identifying signs of stripping at high redshift. And we can identify these by searching for things such as residuals when comparing to a circular velocity model. We can also look for spatial offsets between the CO center and the stellar center to see if ram pressure is strong enough to affect even the most strongly bound gas. You can see the kinematic and gas centroids have an offset. We can also search for if there's a significantly different position angle and inclination in the gas disk compared to the stellar disk. And finally, we can also just look at the overall kinematic properties that we survey, such as V over sigma, to see how high redshift clusters compare to the field and how they compare to low redshift clusters. And with that, I'll take any questions.